Welcome to The Explainer. Today, we're unpacking basic AI for everyone. We're going to bridge the gap between that big 30,000-foot view of how artificial intelligence systems actually learn, all the way down to the nitty-gritty microscopic math that makes the whole shebang work.
So, let's kick things off with the seemingly simple question. How do you teach a machine that a dog is, well, a dog? I mean, a human toddler picks this up almost instantly, right? But for a computer, it is a monumental challenge. This right here is the core puzzle of machine learning and computer vision, and it's exactly the mystery we're going to solve today by looking under the hood.
Here's our roadmap for today. First, how do machines learn? Second, seeing like a machine. Third, the artificial brain cell. And finally, the math of similarity.
All right, part one, how do machines learn? The fundamentals of AI.
At their absolute core, every single learning machine really just boils down to three main parts. Step one is the data. You absolutely have to provide training data for the system to learn from. Step two is a metric. Basically, you need a purely mathematical way to quantify the error, which is really just the difference between what the system spit out and what it actually should have spit out. And step three is the feedback. This is a mechanism, usually something called a backpropagation algorithm, that takes that quantified error and uses it to guide the system toward a better result the next time around. It's essentially this massive, constant loop of guessing, checking the error, and adjusting.
Now, those three foundational steps, they can be applied in a few different ways. Generally, machine learning algorithms are broken down into three broad types: supervised learning, unsupervised learning, and reinforcement learning. The really crucial takeaway here is that in supervised learning, the data we're feeding it is heavily labeled. Humans have already gone in and sorted it into distinct classes. But man, here is the catch. Image annotation is an incredibly tedious, labor-intensive process. To get an algorithm properly trained up this way, you need hundreds of thousands of those training samples. Actually, think about every time you're asked to prove you're human online by clicking on pictures of traffic lights or crosswalks. Yep, you are literally providing that labeled data.
Moving right along to section 2, seeing like a machine, from pixels to features. Okay, so when you or I look at a picture, our brains just instantly get what's going on. But computers, they definitely do not see the world the way we do. To actually process an image, they don't just stare at the raw pixel values. Instead, they rely on features. Think of features as extracted metadata. These can be handcrafted by human experts using techniques with wild acronyms like HOG or SIFT. Or they can be deep features, which are learned totally automatically by deep neural networks munching on massive amounts of training data. At the end of the day, the machine's classifier uses these extracted features, not those raw pixels, to make its final call.
Which brings us right to image classification. The machine's task here is pretty straightforward. It's just sorting whole images into distinct, predefined buckets. It looks at a picture and says, okay, this is an airport, or this is a beach, or this is a forest. It's assigning one single label to the entire image based on whatever dominant features it pulled out.
But then we have object detection, which takes things a massive step further. We are no longer just slapping one blanket label on the whole picture. Now the algorithm is identifying specific items and locating them precisely using bounding boxes. It can pick out really complex, overlapping features in a busy scene, like drawing a yellow box perfectly around a dog, a red box for a bicycle, and a green one for a truck way in the background.
So just to briefly recap the difference before we zoom in even tighter. Image classification simply asks, what is in this image as a whole? Object detection, on the other hand, goes that crucial extra mile, asking, what are the specific objects in here and exactly where are they hiding?
All right, section 3, the artificial brain cell, the micro-level mechanics.
You might be surprised to hear this, but the quest to mathematically model a brain cell is not some new Silicon Valley trend. It's got incredibly deep historical roots. Way back in the early 1940s, literally years before the first modern computers even existed, McCulloch and Pitts proposed the very first neuron models. They envisioned them as these binary thresholding devices capable of running basic logic operations. It's crazy to think about, but AI has actually been building on this exact foundation for over 80 years.
And what's super cool is how directly the abstract math actually mirrors biological reality. Look at a biological neuron. You've got input signals traveling right through a synapse. Now look at an artificial neuron, or a perceptron. Those input signals are multiplied by weights, and those weights act exactly like synapses, determining the strength or importance of that connection. The artificial neuron just takes all these weighted inputs, sums them up, and if that total passes a predefined threshold, boom, the neuron fires an output signal.
Now, to actually pull off this calculation, we have to represent these signals mathematically. We do this using scalars, which are just single standalone values, and vectors. Don't let the word intimidate you. A vector is simply a mathematical quantity that holds more than one element, usually lined up in a neat row or column. Just think of a vector as an organized grocery list of numbers that represent our features or our synaptic weights. Which brings us to our final section, the math of similarity, dot products, and correlation.
Okay, I know dot product sounds like serious math jargon, but it's honestly just a mathematical operation used to measure the correlation or the similarity between two sequences of numbers. That's really it. It's just a highly efficient mathematical way for the computer to ask, hey, do these two things look alike?
Let's actually walk through how this plays out. Imagine we have two perfectly identical sequences of numbers, 4, -2, 6, 3, and -6. To find their similarity, the machine runs a dot product, which just multiplies each corresponding pair and adds the whole thing up. So 4 times 4, plus -2 times -2, plus 6 times 6, and so on. The math here gives us a result of 101. Because our two sequences match perfectly, the calculation spits out a really high score. And that high correlation tells our artificial neuron, yup, absolutely, these features are a match.
But what happens when they don't match? Let's take a new sequence where the numbers are totally different and run that exact same dot product calculation against our original sequence. This time, because the numbers are mismatched, the positive and negative multiplications end up canceling each other out, giving us a much lower score of just 23. That low score mathematically proves to the system that the features just aren't that similar, so our artificial neuron is probably going to stay quiet and not fire.
Now, this simple correlation math is incredibly powerful. As our source material highlights, basic perceptrons can successfully hone in on a solution in a finite number of steps as long as they're trained on what we call linearly separable data. In plain English, that just means the math works flawlessly when a problem can be neatly divided by a single straight line. Imagine being able to draw a single line on a graph to cleanly separate all your apples on one side and all your oranges on the other. That's linear separability.
But guys, that leaves us with a pretty massive cliffhanger. What happens when the real world is just way too complex to be separated by a single straight line? Because let's be real here, most real-world data, like trying to distinguish between a dog, a bicycle, and a truck all in the same frame, is messy. It overlaps in highly complicated ways. This exact fundamental limitation of the basic perceptron is what forced researchers to get creative and develop complex, multi-layered deep neural networks. It is such a fascinating leap from basic math to the incredibly advanced AI we see today. And honestly, it's the absolute perfect place for us to wrap up this explainer. Keep questioning everything and keep learning.